Hi, welcome to Real Learning Center. Today we are going to basically start a new topic called as rotational motion. So rotational motion is about moving without moving from place to place. So it is standing there and moving and rotating. So that's called rotational motion. So in that we are going to cover a topic called center of mass with some basic understanding of rotational motion. We go into the need of the center of mass and what is this, and then moment of inertia, and then we will talk about angular kinematics and torques. Okay, so these are the three different topics we are going to cover under rotational motion. So let's start the first topic. So we have heard about rotation and revolution. Okay, so what are these rotations and revolutions? So what is a revolution? Okay, so we say a revolution means the sun going, the earth going around the sun. We call it as a revolution. And earth rotating on its own axis, we call rotation. So here we are going to basically use a specific case of a revolution, which is called as uniform circular motion. So you can clearly see here that this object is going in a circle. It's a uniform circular motion. That means it is going with a uniform speed. It is not changing its speed. It is just changing the direction. So that we call it as uniform circular motion. So now if you consider this as uniform circular motion, what is the relationship of such a motion like UCM we call, along with respect to rotation? So let's say we're going to stop this at some point here and look at the body here, which is there, which you can see here, an object, and I'm going to add some more such pieces, okay, like this. I'm going to add one more piece here, and I'm going to add some pieces in the middle like this, and gum it up and make finally one single piece like this. Okay, this single piece actually a bar. It contains small pieces, many small pieces glued together. Or on the other hand, we can say any single bar can be thought of as made up of small particles. Okay, so are added together to make one big extended object. And this object, when we make it go in terms of basically rotation, let's say, is like this. So now if you carefully actually watch here, this is our rotational motion. If you carefully watch, one of the particles, which is at the edge, if you say, take it is still going through the same circular motion. Okay, so if you actually look at another particle, it may be going through a circular motion of a different circle. Next particle, different circle. So the radius of these circles are all different. They are all concentric though, okay, at the center. And in the center part, one single dot at the center is not moving at all. Okay. All the others are actually going through the circular motion. And all of them are taking same amount of time to rotate, finish one revolution, one rotation, or one revolution, that small dot. So, uniform circular motion of multiple particles inside a system actually is similar to saying rotation of the whole object. So every particle goes through a uniform circular motion with different radius. That is what we have learned about the relationship between rotation and revolution. So now, whenever I apply certain things to rotation and uniform circular motion, similar thing can be applied to rotation in this sense. Okay. So now, let's look at basically examples of rotational motion. What are the different examples? You know, this is actually a South Indian top, playing top, so which rotates. It's a nice game that people play, children play, and you can see basically this is another kind of a rotating thing. It rotates like this. It's also a game, playing, and you can see actually the wheels that we see day to day. They all rotate, and they also move. They rotate and they translate. We call moving from place to place as translatory motion. At a place, doing like this is a rotational motion. So wheels actually do both of them. They translate, they rotate, both of them. Okay? And you can see the machines and the gears, mechanisms inside the machines, all of them actually rotate. There's a lot of rotational motion involved in our daily life. And you can also see that the whole of our earth actually is rotating on its own axis. So rotational motion is quite universal, everywhere it is there. So we need to understand it and study it. Okay. So now let's start with basically a simple question. What is the effect of force on an extended body? What is the meaning of an extended body? So now first of all, we have always considered an object as a point object. Okay, it's just a small point object. And on the point object, if you actually apply certain force, okay, that force will push the object, you can see. So there is a translational motion when it comes to the point object. Now, if you take an extended object is something which body is something which is not a single point, it's a long one. So you can see an extended object. On this, if I put some force and push, what will happen? So what happens, you can see very clearly here, is that it is not only going a little further, but it is also rotating like that. Rotating. Not completely, but some part rotating. Once the force stops acting on it, it will just keep quiet. So rotational motion happens whenever you apply a certain force on an extended body that we have seen. Okay. So point object just moves, but extended object rotates while moving. It also moves and it also rotates. So that is basically the effect of force on an extended body. Now the question basically is, does it always rotate? Okay, we have seen that whenever you push an extended object like this, okay, it rotates. But does it depend on where you apply the force? Suppose if I apply the force here, exactly in the center, okay, and I apply the force, then you push, then it is not actually rotating, it is moving like a point object. So that means that whenever it does not rotate, if line of action of the force passes through its center, okay, whatever line of action of the force is basically, if you extend it, it passes through the center of the object. When that happens, it actually does not rotate, it moves straight. So now for any real world object, it's not only important to understand what happens when the force is applied, but we also have to understand where is the force applied. Okay, is it applied in such a way that it passes through the center of mass? So we call this as center of mass. So wherever a center of the whole mass is located, we call it as center of mass. So center of mass becomes very important. And you can also realize here that if you go a little further from the center of mass, then you'll start getting the rotation. But there's still a lot of translation moment. But if you go too much further, then what happens? Most of it is rotation and less of translation. So we have to understand here that finding out where the center of mass is an important thing that we need to do before understanding what happens in the real world when we apply force. So we have to find center of mass. How do we find center of mass of any object? So actually center of mass finding is not all that difficult. Now you take any regular object here and let us say the rectangle. So you draw two diagonals and you find a point in between that. Okay, and that point is the geometric center of the rectangle. And if you take, for example, a triangle, you draw medians and they all join at a geometric center. So geometric center happens to be actually center of mass also in most of the scenarios. In some scenarios it is not. I will tell you when. Okay. So now you take also another scenario here. It's a three-dimensional object, and here even those two are also three-dimensional in the sense that there is a small thickness, whereas this one is a big thickness. Okay. So we call it as a three-dimensional object. This one also. So here you join basically two diagonals from this end to the other end, and they will meet at the exactly center of the cube. And the center of the cube is basically where your center of mass is located. So now we will say that if the material is uniformly distributed in the object, then geometric center is the center of mass. That means if you take an object where its material is not uniformly distributed, that means it is thicker in one place, thinner in another place, or it is actually made out of a higher density material in one part and lower density material in the other part. Maybe steel here and some other material, metal, like for example bronze on the other side. Such scenarios, these things don't work. But a regular one single uniform material distributed everywhere, in that scenario, geometric center, whatever you find out, is nothing but the center of mass. We find the geometric center, we find the center of mass. So now let us find out basically what is our mathematical approach to a center of mass. Okay, so in any scenarios, okay, generally we take, I am taking here one shape, some random shape, okay, and I am also considering the fact that it might have, okay, different densities everywhere. So we cannot simply take a geometrical window. Okay, it may be anywhere. It depends on the thickness, everything. So I will cut this into very small pieces. Very small pieces. Okay, so these are all different pieces. Each piece is one small mass. Okay, so there are many small pieces like this. Yeah. So each piece is one small mass, and then I'm going to draw on x-axis and y-axis to find out how far is that piece. Okay, where is that in the coordinates? So this is x-axis, this is y-axis. Now I will take one piece out of it. Let's say the piece somewhere there, one piece out of it. And where is that piece? And what is its mass? So that piece, let us say, has a mass m1, okay, and is at a distance, x-axis distance of x1 and y-axis coordinate of y1. So coordinate of m1 is x1 and y1. So like that we can take, for example, m2, one more, okay, and that actually has a coordinate of, let us say, x2 and y2. Okay. So like that there are many m1, m2, m3, m4, m5, many of them are there, up to, let us say, mn. Okay. So there are so many n particles, n small particles, each one having a certain mass, okay, and each one having a certain coordinate like x1, y1, x2, y2, like that. So in such scenarios, this is a mathematical, very rigorous approach to finding the center of mass. There are simpler methods to find, but we need to know what is the more rigorous method to find the center of mass. So now, how do we find out center of mass? What we will do is, we know m1 into x1, we know m2 into its x coordinate x2, plus m3 x3. Like that we keep adding up to all of them, mn, xn, okay, and then we basically divide that by m1 plus m2 plus m3 plus m4, like that, which is nothing but the total mass of the body. So we'll call it as a capital M if you want. Okay. So this ratio we will call it as x coordinate of the center of mass. This is the x coordinate of the center of mass. If you want to find the x coordinate of the center of mass, this is the formula to use. Yeah, and similarly, y coordinate of the center of mass can be found out by simply m1 y1 m2 y2, like that, mass into y distance, like that we keep adding up to mn. So then we go to divide it by again the total mass, add all the masses. So that forms basically our y coordinate. Now once you get x and y coordinate, you can actually locate it on the picture, that is somewhere x and y, and that we will call the center of mass of the whole of the picture and the object that we have. So this is a method to find the center of mass. Now if you want to practically apply this, instead of making small pieces, we can actually make big pieces for which center of mass we know of, and from there we can compute the center of mass using the similar formula. So let's see how to do that actually. Okay, here xy is the coordinate of the center of mass. Let's take one simple example. So how to compute the center of mass. So I'm having an L shape here. Okay, in the L shape you can clearly see that the thickness is 2 cm here and 2 cm here. The short arms there are 4 and 4 cm. Now where is the center of mass of this? Let's say it has a small thickness. Okay, so I'm going to basically find out the center of mass, for which I am going to draw x-axis and y-axis. Once I draw x-axis and y-axis, what I'm going to do now, I'm going to basically find out how to split this into small pieces. Instead of making small pieces, I will make two big pieces. by drawing one line here. Okay, so two rectangles, one long rectangle, one rectangle like this, two rectangles. And then I will actually find out the geometric center of these rectangles. So the smaller rectangle, I drew two diagonals and found the geometric center. And bigger rectangle also I found the geometric center. So this is the geometric center. So now what I will do is, we know the total mass. Total mass, how do we calculate? Mass is nothing but the volume into density. The volume is area into thickness. This whole area into its thickness is basically the volume. Into the density will give us mass. Okay. For any area we can do that. Okay. Now in this case, we can say mass, for example, of the first one is m1 and mass of the second one is m2, rectangles, two rectangles. So now for m1, we can say, okay, what is the mass of that? So it's area into thickness into density. So instead of writing into, I am writing dots here, okay, just to avoid confusion with respect to x. Okay. So now m1 is equal to 2 into 6, that is length into breadth for that long rectangle, into thickness into thickness into density, T into D. Okay, 12 TD is basically my mass 1. So similarly, mass 2, let us calculate, is its height is 2 and breadth is 4, 2 into 4. Okay, and 2 into 4 into T into D, which is 8 TD, that is m2. So we have found out basically masses of each one of these rectangles. We have also found out the geometric center of each one of these rectangles. Okay, so it means they are the center of mass for those rectangles. So each rectangle center of mass we know. Each rectangle's mass we know. Okay, so now how do we use that to calculate the overall center of mass? So for that, first of all, we will locate this, where this is. Okay, so we will say that this length, or what we call, is x1. The center of mass for the first one is x1, which is 1 centimeter. You can see, because it's half of the width. Y1 is let's say 3 centimeters, because total is 6 centimeters. So we can similarly do the second one, draw a line there and find out basically x2 is 4 centimeters, where it's located, center of mass, and y2 is just 1 centimeter. Okay. Now let us write m1x1 plus m2x2 divided by m1 plus m2. So that is basically our what we call center of mass, the x coordinate. X coordinate is m1x1 plus m2x2 divided by x1 plus x2. So let's substitute the values. When you substitute the values, what you will get? You will basically get the 12 into TD plus into 1, that is 1 centimeter. 8 into TD plus 4 centimeter, all divided by 12 TD plus 8. So this actually I will take, and you take the TD common and remove. Thickness and density will get cancelled. Okay. So if you compute this, you will basically get 2.2 centimeters. 2.2 centimeters is the x coordinate of center of mass. Same way, we can calculate the y coordinate of center of mass. How do you go about doing that? You do m1 y1 plus m2 y2 divided by m1 plus m2. So that is nothing but the y coordinate. And we know y1 and y2 also. Okay. So substitute that into the same formula, and we know the masses. We substitute it and we calculate the value of capital Y, which is nothing but the y coordinate of the center. So that we got it also as 2.2 centimeters. And naturally so, you can see that this is actually symmetrical on x side and y side, and it cannot be very different. Both sides are 2.2 centimeters. So now we can actually say that the center of mass is nothing but xy, which is 2.2 comma 2.2. Now if you actually want to locate where that is in the L shape, you can see 2 is the height and 2 is the width of this L shape, and it is little more than 2.2. So that is where the center of mass. And you will be surprised that in this scenario, the center of mass lies outside the body. The body is just this much, L shape. The center of mass is outside the body. So it is possible that the center of mass may lie outside the body. Remember this. Okay. Still we call it as the center of mass of this body. So this is how you calculate the center of mass. Now it is possible to extend the center of mass to 3-dimensional scenario. I just showed you for simplicity's sake a 2-dimensional scenario. But you keep a 3-dimensional object, and then you have 3 axes, x, y, and z. And then what happens is you can do m1 x1 plus m2 x2 plus m3 x3 like that. You can go and call it as basically x. Similarly, you can do y by basically taking it. Now there is, if you split into multiple small pieces inside the cylinder, each one is m1 is a small mass of a small piece. Okay, like that you can do for the y coordinate also. So you y coordinate, these two are similar that we have already discussed. So z is nothing but one more coordinate. So now you talk about m1 z1, m1 z2 plus m3 z3, mn zn divided by m1 plus m2 will give us the z coordinate. So now once you calculate all these z coordinates, x and y z coordinates, you can locate it in the actual picture. Okay, the x distance to the center basically you measure on the x axis, that is x, and then you measure on the y axis is y, and you measure on the z axis is y. So it is at the geometrical center of the cylinder. This is how you can do calculate the center of mass of a 3-dimensional object also. So now let's actually give you some small homework. Now try these things. So I have actually an object which has a rectangular piece and a circular piece of a given dia. Okay. So please find out the center of mass for such an arrangement. Okay. So using the same formula, whatever we have in the data. And one more you can do, the second one. This is very straightforward, you can do it. And the second one you can do is, here is one circular plate, okay, from which a circular hole is cut, and that hole is cut in such a way that the diameter of the hole is nothing but the radius of the bigger plate. Okay. So it's cut out. Now can you find out where is the center of mass? Because if you don't cut it out, geometrical center or the radius, center of the circle will be the center of mass. Now when you cut it, where does it move? So please find out that. Here it is a tricky because you see it is very hard to take so many pieces inside this and find out where they are. So now you need to use a technique called as subtraction. So you have to take the center of mass like you m1 x1 minus m2 x2 instead of plus. If you do for these two circles, you can actually calculate. That's a technique for that. So please go ahead and try that and see whether you can find the center of mass for such a scenario. Okay. So now having covered the center of mass, we now move on to, then in the next session, we now move on to moment of inertia, okay, which is also an extremely important concept in the rotational motion. Then we address the rotational motion directly in terms of angular kinematics